I had cautioned you earlier that we had been working with an extremely simplistic model of the MOSFET and that its behavior in real life is considerably more complex. And in fact, over the next few minutes, we will look at a kind of the next level model for the MOSFET, which is slightly more accurate, but it's still a gross simplification of the actual behavior. Okay, it'll be several lectures before we will cover a much more closer representation of the MOSFET looks like. But as a next step, let's do a slightly more refined model of the MOSFET, and here it is. In our previous simplistic model called the S model or the switch model of the MOSFET, we simply said that the MOSFET was an open circuit when VGS was less than VT. Between the open circuit was between the drain and the source voltages when VGS was less than VT. So this was an open circuit. For the S model, for the switch model, we said that when VGS was greater than VT, we had a short circuit between the drain and the source, and that was true for the when we had taken a very, very simplistic model. But in reality, what happens is that when you apply a high voltage at the gate with respect to the source, we don't actually have a short circuit. Rather, there is some finite resistance between the drain and the source, and we call that R on. So the MOSFET turns on. So the MOSFET is in its on state, but even though it's in its on state, but there is some resistance between the drain and the source, and it's not completely an ideal switch. And so, for example, R on might be on the order of 5 kilo ohms. Now, depending on the kind of MOSFET you have and the technology you're using, whether you're using a discrete device or using a MOSFET device within a chip, the resistance can change. You can also change the size of the MOSFET and make the resistance of the MOSFET bigger, lower, or higher, much like you could change the resistance of some piece of material by making the material wider and longer, and so on and so forth. But the SR model for the MOSFET says that in its on state, there is a resistance between the drain and the source, and in its off state, it behaves like like our usual switch, which has an open circuit between the drain and the source terminals. So with the SR model of the MOSFET in mind, we can actually go ahead and plot the IDS versus VDS curves for the MOSFET. So let's start with just as reference, on the left-hand side of this line, you see the MOSFET characteristics, assuming a very simplistic model for the MOSFET. Okay, we had a really, really simple model for the MOSFET. The MOSFET behaved like an ideal switch. Then you would see the model shown on the left, where the VDS versus IDS relationship would be either reflective of an open circuit or a short circuit. I should write this as small VDS, and this should be small VDS as well. So this is VDS, and this voltage between the gate and the source is VGS. Similarly here, VGS between gate and source, and VDS between the drain and the source terminals. So for the very simplistic switch model, you saw the IV curve for the drain and source terminal as shown, and because the MOSFET had two states, so this was its on state and this was its off state. Okay, depending on the state, you got a different value for the IDS versus VDS curve. Now let's look at what it looks like, the IDS versus VDS for the MOSFET, assuming the slightly more accurate model, the SR model. So in this case, when VGS is less than VT, the behavior is still zero here. Behavior is still the same. It's that of a open circuit. Okay, so that doesn't change. However, when the VGS is greater than or equal to VT, I don't get a perfect open circuit. Rather, I get some resistance between the drain and the source. Okay, so this begins to behave more like a small resistance, and the resistance here is given by R on. So the conductance is 1 divided by R on in this IDS versus VDS curve. So but there you have it. So this is the IDS versus VDS curve for the MOSFET under the state that VGS is greater than VT. This is the on state, and this is the off state. Let me now show you a quick demo showing you these curves, and show that as I switch the MOSFET on and off by applying either a high voltage or a low voltage between the gate and source, you will see the curves that look as I've shown you just now.